Section 10.4 Macroscopic Description of an Ideal Gas. Objective 1. State the properties that define an ideal gas, and Objective 2. Apply the ideal gas law to systems of gases. Let me start by giving the ideal gas law. The ideal gas law says that the pressure times the volume is equal to the number of moles times the ideal gas constant times the temperature in Kelvin. So once again, that's pressure in pascals, volume in cubic meters, number of moles and just in moles, and R is the ideal gas constant, 8.31 joules per mole Kelvin, and this is constant like other constants that we've had before. T is the temperature in Kelvin. This is the absolute temperature, so 0 represents like complete stop, no molecular energy in the gas. No kinetic energy in the gas. I will be soon adding another part of this that goes 2U over dF. And essentially what the internal energy is, the U, it includes a linear kinetic energy part, rotational kinetic energy part, and a elastic energy part. And dF stands for degrees of freedom. And what the degrees of freedom is usually, or for a particle that does not rotate or stretch, you have 3 degrees of freedom because you got v sub x squared plus v sub y squared plus v sub c squared. A lot of times for things that have rotational momentum, they can actually rotate around 2 axes at once, so you get another 2 there. And sometimes you get a particle like carbon dioxide stretches along the long axis, so you get another 1 degree of freedom there. In our text, you'll find that they will end up putting a 3 here, and they only talk about monatomic gases, and they're not quite so general with the formula. One thing I have not explained yet is what is a mole. A mole is a number of particles. The number of particles is 6.02 times 10 to the 23rd particles in a mole. And if you want to know how big that number is, I was working out some things and figuring out that it is the number of cubic millimeters in a cube that is 84.4 kilometers on a side, and that is also 52.5 miles. And then I did the same thing with working it out with an r cubed and finding out that it's same as the number of cubic millimeters in a sphere 105 kilometers across. So it's a big number. Now let's put that in perspective. That number of hydrogen atoms weighs 1 gram. I'll pull up a periodic table of the elements on Wikipedia, and you can see hydrogen, technically a mole of it weighs 1.008 grams. Helium is 4.0026 grams. Lithium 6.94 grams. Beryllium 9.0122. Now, the unit is based on something called carbon-12. This 12.011 represents a common mixture that happens in Earth's crust, probably. There are 3 isotopes that occur naturally: carbon-12, carbon-13, and carbon-14. Carbon-13 is stable, carbon-12 is stable, and carbon-14 decays with a half-life of about 5,730 years. So looking up carbon-12 specifically, you can see down here isotope mass 12U. And it would be the same if you said 12.00000U, because this carbon 12 is actually the definition of U. I'm sorry, this is the definition of the mole. The mole is the amount of substance of a system which contains as many elementary entities as there are atoms in 12 grams of carbon 12. So this 12U for isotope mass here is not uh, exactly the mass of carbon 12 so much as it's the definition of the mole, i.e. the number of carbon 12 atoms that weigh 12 grams. Okay, the textbook talks about how this relationship is very convenient, looking at the periodic table of elements at the back of the book, blah, blah, blah. I don't think it's convenient at all because they have not assigned a variable to isotope mass. What is the standard convention for using for isotope mass or atomic mass? So here's what I do have. Wikipedia called it isotope mass. Our text calls it molar mass. The unit can be given in U or it could be given in grams per mole. Our textbook actually writes out molar mass in one of the examples where it's given as a unit or as a variable. So for instance, here in 10.7, you would have grams divided by grams per mole and end up with moles. And here, molar mass is grams per mole, and Avogadro's number is particles per mole. So you would end up with grams per particle. In this equation, you can just replace N with grams per mole all the way across. N sub A is in particles per mole. Or no, moles per part. Okay, looking at it a little longer, I think just this equation, it's not right. Because here you've got N sub A times 12U, and then they got an equal sign, and then they say N sub A times 12U times this thing here. So somehow this quantity came from nowhere. So I'm just going to put a big X through that because I don't think that part's valid. It doesn't come out with the right units for one thing. Anyway, I think what I'm going to do is I'm just going to make up a variable for this thing, and it's going to be a big cursive M for molar mass or isotope mass, and it will be either in units of U or grams per mole, and that will be what M is. And you can look and see on most periodic tables, our big cursive M is this number that has all the extra significant digits. So you can look up your molar mass, big cursive M, in the tables, just like you've used for other tables. Okay, so we've got this PV equals nRT, and I've told you that R is 8.31 joules per mole Kelvin. They do a thing where they find what is R in atmospheres. Let's see. So let's write this 8.31. Joule is a pressure times a volume. So I'm going to write that in Pascal meter cubed per mole Kelvin. Basically, pascals times meter cubed is going to convert to joules if you just kind of work out the units. So then I'm going to write down how many pascals is in 1 atmosphere. 101,300. And how many uh, cubic meters is in a liter? There are 0.001 cubic meters in a liter. So, but we're not going to use 101,300. We're going to use just straight 100,000. And when we do that, we get the value that they have here. R equals 0.0821 liter atmospheres per mole Kelvin. So that is another value that they use. And what if we wanted to use PV equals nRT, except think of it in terms of the number of particles? PV equals N is equal to the number of particles, which is the number of particles divided by Avogadro's number. So I'm just going to replace N with N over N sub A. What if I wanted to take the PV equals nRT and make it so we are keeping track of the number of particles instead of the number of moles? The number of particles is Avogadro's constant times the number of moles, so N equals capital N over N sub A. So replacing the little n with capital N over N sub A, and then taking those two constants and combining them, I'll get 8.31 joules per mole Kelvin divided by 6.02 times 10 to the 23rd particles per mole, which cancels that out, and we end up with 1.38 times 10 to the negative 23rd joules per particle Kelvin. And this actually has a name. It is called K sub B, or Boltzmann's constant. I think it's Boltzmann's constant, is it? Yeah, right there, Boltzmann's constant. 1.38 times 10 to the negative 23rd meter squared kilogram per second squared Kelvin. They left out particle, but otherwise it's Boltzmann's constant. It's otherwise joules per Kelvin per particle. And for some reason, people don't think that particles are a unit value, but so they just express it as joules per Kelvin. So you may sometimes see this PV equals N R over N sub A T written as N K sub B T. So that's another way it gets written. With K sub B is 1.38 times 10 to the negative 23rd. Okay, I'm pretty well done with section 5, was it? 4. 4, but I think I'll just do a little example. What's the moles per meter cubed of air? So we're going to use PV equals nRT, but I'm going to solve that for N over V. Anyway, the pressure is generally considered to be 101,300 pascals. R is 8.31 joules per mole Kelvin. And temperature is going to be, we'll call it, well, take 273 plus 20, so 293 Kelvin. So 20 degrees Celsius and 101,300 pascals, which puts it at 41.6 moles per meter cubed. Now you may remember that in an earlier chapter they were telling us that the density of air was 1.29 kilograms per meter cubed. So what would be 1.29 kilograms per mole? So let's look at this. This is the density, or this is the number of moles per volume. This is the mass per volume. And the molar mass that I was talking about earlier was the mass per mole. So I think I can take, so let's call this rho sub m and let's call this rho sub n. This is the molar density and this is the mass density. And so we're going to take rho sub m, the mass density, divided by the rho sub n, the molar density. 1.29 divided by 41.6. This is going to be in kilograms. This is going to be in moles. So this comes out to be 0.031 kilograms per mole, or 31 grams per mole. Now, how does that stack up? Our atmosphere is made up mostly of oxygen, which has a 16, and nitrogen, which has a 14. We just got 31. How does oxygen and nitrogen work to make up 31? Well, it turns out these two gases appear in diatomic structures. So nitrogen has a molecular mass of 28, and oxygen has a molecular mass of 32. So that would suggest that there's more oxygen, but there's also this other substance in there that's not often mentioned, argon, which has an atomic mass of 40, which pulls up that average. And there's about 70% nitrogen, about 29% oxygen, and about 1% argon, and the rest is a bunch of trace gases.